We're now going to find absolute maximums and absolute minimums for a surface function. If we're given a surface function that is continuous over a closed and bounded region in two-dimensional space, then we're guaranteed that that surface will attain an absolute max and an absolute min at some point within that domain region. So here we have a closed and bounded region in the domain. So for this surface, f at x, y, we know that we're going to somewhere in here get an absolute maximum, and we can see by this illustration that that would be happening right about here. Now, because this region in the floor is closed and bounded, we're also going to get an absolute minimum on that function, and it's going to be all these z values right here. These are the lowest z values on the surface. This region has to be closed in order to guarantee that we actually arrive at this minimum z value, and that z value would be the absolute minimum. So let's take a look at some potential domain regions in the xy plane, and we could have a two-dimensional domain region that is closed, meaning that we get all these points in here and the exterior curve is included, but because it is open at the top, we would say that this is not bounded. We could have a domain region that's bounded, meaning that we wrap around all of the domain elements, but not be closed, because that outer curve is not solid. We could have a 2D domain region in the floor that's not bounded because the region is open at both ends here, but also not closed because the lines are dotted. The only region that can guarantee we have an absolute max and an absolute min would be a region that is both closed and bounded. So let's look at an example here. We're asked to find all of the extrema for this function, and that means the relative max, the relative min, the absolute max, the absolute min, and any saddle points. We're given a closed triangular region in the floor with these vertices, and here's the surface function in question. The first thing that I want to do is get an image of the domain. So I'm going to do that both in 2 dimensions and in 3 dimensions. So in the floor, we've got these 2-dimensional points, and we are a triangle in R2. But I'm actually going to label those points with ordered triples since I have graphed it in 3D. Now, it's also going to benefit us to have this graphed in R2 and not just in R3 for some of our upcoming calculations. And so here we have that same closed and bounded domain region. The next thing that we're going to do is we're going to find all the critical points in the interior of this region. We're also going to be exploring the edges of this region, but the first thing we'll do is start with the interior. Now, to find the critical points for this surface, we're going to need to look at where the first partials are equal to 0. So we take the first partial with respect to x. This derivative is just going to be y. This derivative is -1. So now the first partial with respect to y holding x constant. This derivative is 0. X is a constant here, so this derivative is just x, and this derivative is -2. So we set each of these first partials equal to 0. So this one is going to be just that y is equal to 1, and here we have that x is equal to 2. So our critical point is just going to be the one-ordered pair 2, 1. And just to make sure that that is inside our region, we see 2, 1 is an ordered pair right here. So we definitely need to consider this for extreme values. Now let's come down here. We're actually going to begin a master list of ordered pairs within this domain region that we're going to be testing to determine what their corresponding output values are and determine whether they are the highest or the lowest in this list of potentials. So we've already determined that 2, 1 is somebody to be considered. So we need to evaluate the function at 2, 1 and see what that z coordinate is. As a reminder, our function was 3 plus xy minus x minus 2y, and so our function evaluated at 2, 1 is going to be just 1. Now, we are going to take any critical points from the interior and we're going to evaluate that second derivative test at the critical points to determine whether they're maxes, mins, or saddle points. So let's come back up here and remember that this was our first partial with respect to x. This was our first partial with respect to y. So if we evaluate this first partial with respect to x again, we don't have any x's in there, and so this is actually going to end up just being 0. If we evaluate this first partial with respect to y again, we don't have any y's, so again we get 0. So now let's look at the first partial with respect to x and differentiate it with respect to y, and then this partial derivative is just going to be 1. Let me stack these up and simplify the notation a tad bit. Now, they're all constant values, so when I evaluate this second derivative at 2, 1, we're just going to get 0 here times 0 here minus 1, which is going to be negative 1 less than 0, and the second derivative test tells me that we end up with a saddle point. So back down here in our master list, let's just indicate that. So that's all that's happening on the interior. So now we're going to want to check each of these boundary lines. Let's see if we can conceptualize what we're about to do. We're looking at this boundary line here. We're going to say, where are the potential maximums and minimums along this boundary? Which means that if I were to fly this boundary up to the surface, I would want to see what the high points and the low points were along that boundary. Well, those high points and low points would exist along the intersection curve between the boundary plane and the surface. So we need to find that intersection curve C. And the way that we find an intersection curve is to substitute the plane equation into the surface equation. So the plane equation that we are using here for this boundary is the plane y is equal to 0, which runs along that x-axis. So if we were to plug y is equal to 0 into our surface function, we're going to get 3 plus 0 minus x minus 0. So let's just call this 3 minus x. And as a matter of fact, this is actually just a function of x because y is a constant 0. And if I rewrite it like this, it's easier to see that this intersection curve is just going to be a line. So let's adjust our concept drawing. Again, this is not exactly perfect. It's just kind of helping us to get an idea. But if that intersection curve is a line, then we know that the extreme values are going to occur at these endpoints. So the domain element 5, 0 and the domain element 1, 0 need to go into our master list because these are potentials for extrema. So for 5, 0, we're going to have negative 2. For 1, 0, we'll have positive 2. So let's slide these over here. Now, these values do not get plugged into the second derivative test. The second derivative test is only for critical points, whose first partials were equal to 0 or undefined. That's not these two. These two are on the boundary. They are the high and the low point of a line. Now let's look along this boundary and fly it up to see how this one intersects with the surface as well. It could be a curve, it could be another line. We'll see. Since we don't know yet, I'm going to leave that off and say that we're looking for that intersection curve, but we're not sure what it is yet. In order to determine how this boundary plane is going to intersect with the surface, we're going to plug that plane equation, which is x is equal to 1, into the surface. So if we plug the plane equation x is equal to 1 in here, we're going to end up with a function that then only depends on y. So 1 goes in for x, nothing in for y, 1 goes in for x, nothing in for y, and our function now only depends on y. And essentially, this is going to give me a z output, and we'll say it's negative y plus 2. It is another line. So up here on my concept drawing, I'll just indicate that it's a line. Of course, again, this is not entirely accurate. This is just giving me an idea. Our surface functions graph does not look like this, but concept drawings really help me to kind of gain some intuition about what happens next. Now, because that intersection curve is a line, I know that the extreme values are going to occur at the endpoints. So we just need to make sure that both of these endpoints are in our master list. 1, 0 is already in the master list, but 1, 4 is not. So we need to determine who is the output on the surface at the domain element 1, 4. So this is 7 minus 1 minus 8. That is negative 2, and we're getting somewhere with our master list. Now we need to check this last boundary here, the hypotenuse side of our triangular region. And so essentially we need to figure out what this plane equation is. When we fly this up to the surface, we need to see what kind of an intersection curve we're going to have between this diagonal plane and the surface. To determine this intersection curve, we need the plane equation. We would then plug that plane equation into the surface to see what the intersection curve is. To get the plane equation, let's look back over here in R2. And the equation of this line turns out to be negative x plus 5. And I did skip a few algebra steps there. So that's the equation in R2. It's actually also the equation in R3 because y is equal to negative x plus 5 in 3 dimensions is going to fly up and down in the direction of the missing variable, which is z, giving us that plane. So we essentially are going to take our surface function and plug negative x plus 5 in for all the y values, which is basically taking this equation and plugging it into our surface function to see what that intersection curve would be. And so we have 3 plus x times y, which is negative x plus 5, minus x minus 2 times negative x plus 5. So we can simplify this notation to say this z value actually now just depends on x, and we want to simplify it more over here on the right. So we have 3 minus x squared plus 5x minus x plus 2x minus 10. So our intersection curve C3 turns out to be a parabola that opens down within this plane. And an opening down parabola is going to achieve a maximum value at the vertex. And there's a couple different ways that we can find that vertex point, but let's use the algebra way, which is to look at the value negative b over 2a, which in this case would be negative 6 divided by 2 times negative 1, or positive 3. Then we take that value and plug it back into the function to get the corresponding output, which is positive 2. So before we determine who goes in the master list, let's decide who these variables are. Remember, of course, this is our x-coordinate, but is this output up here a y value? Actually, it's a z value. Remember where it came from. We let y be equal to negative x plus 5, but this output is the output value on the surface. This vertex point has an ordered pair in the domain whose x-coordinate is 3, but the output of this function is a z-coordinate. How do we get the y-coordinate to complete the domain point? We would plug 3 into this equation. So our domain element is 3, 2. I'm going to put 0 in here because we're at the floor. And this flies up to a point on the surface that is 3, 2, and it turns out that the z-value is also 2, so that's our ordered triple. So to complete our master list, we had 3, 2 as a domain element, and the function evaluated at 3, 2 was 2. So we've tested all the boundaries and the interior. And in our master list, we notice that these two are the lowest quantities, so these are going to be absolute mins. These two are our highest quantities, so these are going to be absolute maxes. So let's summarize to say the absolute min is negative 2, and it occurs at two different domain elements, 5, 0, and 1, 4. The absolute maximum is positive 2, and this occurs at two domain elements as well, 1, 0, and 3, 2. We also ended up with a saddle point, and let's just say that this was the ordered triple, 2, 1, 1. So this is our final answer.